Thank you for the introduction. As Jorge mentioned, my name is Pavel Michailov. I work in the Microsoft Identity Division. My talk today is about some of the challenges that we've had in running large-scale services and the fault injection that we've used in order to address some of these challenges. So what are some of these challenges we've faced? Well, the big problem, especially in identity services, is that we are in the critical path for many upstream products. So even a short outage on our end can cause a disproportionate financial and reputation cost to the company. So as a result, our goal is to have uptime that is as close as to 100% as possible. No degradation in service, and a service that is responsive to failure in either some of its downstream components or other transient problems. Now, one of the challenges as well with cloud services is deployment. So when we think of how services work compared to boxed products where an engineering team will build the product for several years sometimes, and then a testing team will test it for several months. Cloud services evolve much faster. You have deployments that are as frequently as days, sometimes hours, sometimes continuous deployment. And not only that, they're not as monolithic as box products. You have many services deploying at the same time and all interacting with each other. So each of the services in this mesh has to be able to tolerate the failure of its downstream dependencies. Now, so some of the testing challenges with cloud services, so I mentioned the first two already. This is continuous evolution and the fact that there are multiple dependencies involved. But it's also that services are deployed worldwide in multiple regions with traffic that fluctuates throughout the day or throughout the week. And sometimes, even after a deployment is complete, it's not immediately obvious that there's been a regression introduced. So in order to address some of these challenges, the Microsoft Identity Division has implemented a fault injection system to test some of these scenarios. So it works by, now just to mention that I'm not a developer, a core developer in the fault injection system team, but I've worked with them closely, so I'm familiar with the system itself. So the goal is to inject faults into a deployed service and verify that the response of the service is what it should be, and thus overcome some of the limitations that we have from traditional testing, so like unit tests or functional end-to-end tests, which just don't have the kind of coverage that we need. So I'd like to break this talk up into two parts. I'd like to discuss first the fault injection system, what it can do, how it works, and then go into some of the applications that we found for it in our stack. So this is a high-level view of the system architecture. We have on the VMs, we have fault agents running. These fault agents have all the code necessary to execute a variety of different faults. Moving slightly outward, we have the cloud management service. So in this case, these are primarily Azure APIs that we use in order to do outside-in fault injection on the VMs. So for example, we can trigger stop commands, restart commands, maybe reimage the VMs. And coordinating all of this is a fault management service. So this service takes in requests from the users or from an automated scheduler, and then injects them on one or more of the VMs for the appropriate duration. So there are a number of different kind of faults that we have implemented. I'd like to discuss some of the more important ones. So we have resource pressure faults. So this is really, for example, CPU pressure. We would inject high CPU into a machine for a given amount of time, which is a nice way to simulate, for example, it's a cheap approximation of a sudden spike in traffic. Or, for example, we would have, using the CPU pressure, we can simulate, for example, a code path that may have been written inefficiently and causes a sudden spike in CPU during the operation of the service. We also have memory faults, which are also good for testing edge cases in the code, for example, a slow memory leak or maybe some code paths that all of a sudden can have an explosive effect on and consume the memory on the machine. And we want to make sure that, again, the service can handle this to at least some extent if the damage is somewhat localized. Finally, we have hard disk pressure faults. So these would simulate, for example, the hard drive running out of space or excessive reads and writes to the disk. We've observed this in practice, that some software, some of the components deployed on a VM might not necessarily react very well to the machine running out of space, and all of a sudden we'd observe very strange behavior. So this is something that is very useful to run regularly. Now, another category of faults are network faults. So here we have the ability to inject a disconnect or latency at the TCP level. We can affect some IPs or do a blanket injection where we would intercept all packets incoming to the machine. And this is very useful for simulating perhaps network connectivity problems, as the name implies. But also if there is a problem in one of the downstream services where it's responding more slowly, perhaps due to some bug on their end, this is very useful for simulating that as well. We also have process faults, so these are relatively straightforward. These are primarily OS operations to kill a process, restart the process, crash it with some kind of unhandled exception, or maybe hang one or more threads on the process at random just, to see what would happen. Moving slightly outward, we have a virtual machine and OS faults. So I've mentioned some of these a little earlier, so we can trigger stop, restart, reimage of a machine, make a machine hang. And interestingly, we can also change the system date on machines. And this is very useful, we found, to test edge cases related to, for example, leap year, or, for example, move the calendar on the system forward to verify the behavior when certificates expire and see whether or not the problem is reported. Another very versatile category of faults are application-specific faults. So the fault agents on the machines can intercept code at runtime and override either the return value or throw an exception straight out of the method. And this is very useful compared to the big hammers that I just covered, because an engineer on a specific service team can do a very fine-tuned injection to verify maybe a disaster code path that would normally not be exercised. And finally, if those faults didn't do the trick, we have partner teams that are contributing to the fault agent. They develop faults, they're introduced into the fault agent after a security review, and they can cover some more specific scenarios that partner teams would like to test. So there are three main injection mechanisms that we have. So I've touched on this one already. So this is external injection. So this one would be via Azure APIs, triggering operations at the VM level. We have internal injection. So this is via the fault agent that is deployed on the machines. And finally, this one's slightly out of the scope of the fault injection system, but developers can introduce hooks manually into the code that can be triggered via, for example, a query string parameter or via configuration upload. And this instrumentation is slightly more clunky than the approaches I mentioned earlier because it pollutes production code with testing, essentially testing code. So as it's probably clear by now, this kind of system gives enormous power to the users, so it's very important to secure it correctly. It's integrated with Azure Active Directory. It supports granular access control so that users can only perhaps inject into some of the environments or only injects a subset of the faults. Also, the communication between the fault management service and the fault agents must be secure, because otherwise fault injection requests can be spoofed and bad actor can deliberately cause an outage if this is not secured correctly. And finally, it's very important to have the ability to stop these faults on demand via kill switch or via automated removal in case connectivity to the fault management service is lost. So I'd briefly like to talk about some of the applications that we found for fault injection in our stack. The first of these is resilience verification. So the way that we set this up, we have a number of automated regression tests that run periodically, and along with them are verification scripts that verify that the response of the service is correct to a given fault, that alerts fire, that the telemetry shows that there is a problem. So this is actually an example of some of our daily runs. You see here 2 network faults, a CPU pressure fault, a memory pressure fault, and these really run every single day with associated conditions that must be met for the verification to succeed. Otherwise, the problem is reported. So one of the very important things that we need to verify when running a fault is that proper alerts are generated in case of some kind of failure. And so to do this, we have integrated the fault injection system with our internal alerting. And so as a fault runs, we can configure that we expect some alerts to fire, some alerts not to fire during the course of this fault injection. And finally, because this produces a lot of noise, there is automated incident mitigation and resolution to make sure that the on-call engineers don't have to deal with the extra volume of alerts coming in. So this is actually a good example of fault injection in progress. So what we've injected here is a network disconnect, I believe. So as you can see, we've injected it onto only one data center. And during the fault window, the network latency has significantly increased in that data center. The number of errors coming from it has also increased. And obviously, the quality of service has gone down. So this is, by capturing this information and then verifying it, we can check that the telemetry stream is showing that there is indeed a problem and that it's not gone unnoticed. But we can also verify that, as you can see in the middle tiles, the RPS to that problem data center has dropped significantly, and that is because a failover was initiated shortly after the fault was injected. And so this is also something that's very useful to verify to make sure that there was no regression in the failover mechanism at some point that we did not catch. Another slightly more specific example of what we've used fault injection for is we created 2 custom faults, one to create a local user on the VM, and another to place a malware ACAR test file on the VM. And both of these should result in a high severity security alert firing. And it's also very important to test this frequently, because otherwise, if there is a regression somewhere in that pipeline, this information may be lost and we may be exposed to security vulnerability. So as useful as it is to do regression testing, it's also very useful to use fault injection for verifying new features as they're being rolled out and tested. So a developer or engineer that works on a feature that might have service level impact will select a few relevant faults and inject them when the feature is enabled and when the feature is disabled, and verify that there is no new problem with this feature. And Also, the existing regression tests are very useful for catching problems and new features, and we've observed this recently where during the course of automated regression testing in one of the services, an upstream service which was testing a feature hit an edge case after which there was a resource leak from this feature. And without this suite of tests, it perhaps would have not been possible to discover this on time, and the problem would have occurred during and already in production. So there are numerous challenges to developing these types of tests, and the problem is that unlike unit tests, which by definition mock out every single dependency except for the unit under test, here we are doing system testing. So in the example I gave earlier with the network latency fault, we are testing the alerting system, the telemetry stream, the service under test, and the failover mechanism. So if there's any unrelated problem in any of these systems, this may produce a false positive. And so the more complex the scenarios that we're trying to test become, the more difficult it is to do it in such a way that testers and engineers don't constantly have to deal with false positives. And finally, because we're dealing again with a real system, these tests are very time consuming. So when writing unit tests, it would take milliseconds to verify that it works correctly and iterate until it's done right. But when doing a fault injection test, it may sometimes take minutes for one iteration to happen. And as a result, this can easily take hours if the test is not planned correctly. Another big challenge is adoption. So the full benefit of fault injection can only be seen when it is applied across multiple services in the stack. But because each one of these services has different service owners with different priorities, it's sometimes difficult to get the traction to onboard fault injection across an entire service tree. And oftentimes another problem is that the immediate bang for the buck is not as clear as in cases such as fixing a regression, fixing a bug, or rolling out a new feature. So people will deprioritize this kind of work in favor of, doing stuff that they can easily take off in their to-do list. And the final topic that I would like to touch upon, and this is something that we've been doing for, I think, over a year now, these are recovery games. So this is a weekly exercise which we run between an attacking team and a defending team. So the attacking team will spend the week identifying an interesting fault, and then during the game we'll inject it, and the defender's job will be to try as quickly as possible to mitigate the problem and to first understand the problem and then provide a mitigation plan. So what goes into these recovery games? First, there's planning. So the attackers will need to try to think of a good fault to inject for this game. They do this by perhaps looking through previous incidents, recent incidents that would show that would be a good exercise, or by just trying a few random faults, maybe sometimes several faults at the same time, and see if there's a learning opportunity in there. Once they've developed and tested the fault, the games begin. The attacker will inject the fault and provide more and more explicit hints as the game progresses, and the defender will try to assess the impact and provide a mitigation plan. Now, obviously, this is not the same kind of pressure that is experienced during a real outage. So in order to simulate some of this pressure, we invite as many senior team members and managers as possible to observe this game, and this creates some of the strain that happens during a late night outage. And so what are the goals really of these games? So at least in the identity division in Microsoft, we have our on-call engineers coming from the pool of core developers. So sometimes it'll be months between rotations for each engineer coming in on call. And these skills that are required to do analysis and mitigation of an incident are very different sometimes from feature development. And so in order to get some of that rust off, we place these engineers in this controlled scenario, and they could do log analysis and telemetry analysis and really sharpen those skills before, hone those skills before their on-call rotation. So another very useful side effect of recovery games is that without fail, I believe, every single recovery game has uncovered gaps in the system. So whether it be in monitoring and logging, or dashboards missing data, or some kind of knowledge or process gap. For example, mitigation steps were not properly documented in the wiki. And each find like this in advance helps lower the time to mitigation during a real incident. So this was actually the meat of what I wanted to discuss. I hope I have convinced some of you that fault injection is indeed a useful technique, and I thank you very much.
Interesting. So identity group do some resiliency modeling, I believe, on Azure, that they look at the dependency and relationships between components and so on. Does that analysis provide any input as to what kind of faults you inject?
I am unfortunately not aware of this kind of dependency analysis that you mentioned.
Okay.
I do know that when we select the faults to test, we really base ourselves on, we produce a map internally of all the service interaction. I don't know if this is what you were actually referring to. Okay.
Yes.
So we produce a map of the services that interact with each other, and so using that we've sometimes found very surprising dependencies. We're like, really? That talks to that? We didn't know that, all right. So we would go through this map, and yes, we will pick out interesting victims that we would then inject network latency against, for example.
Okay, because that's the interesting one. Just the second one is that I know you do some model checking as well, using Modist is a method you've applied on Azure. So I don't know if you know the answer, if the result of that analysis also come up in this, the faults that they find in the distributed system.
So I'm fairly sure I do not know this topic,
Okay.
but if we take it offline, maybe you can give me a bit
Sure.
more context.
No problem.
Just a clarification, you say that you run the fault injection on the deployed system.
Yes.
On production deployment,
Okay.
and further, when you do the games, do you do them on production deployment or in some kind of sandbox environment? Thanks.
No, unfortunately, the voices of reason have prevented us from doing large-scale exercises in production. So we limit ourselves to the pre-production environment, which, however, is a very good simulation. In fact, it's connected to all production dependencies except for the one service, which is in test mode. And it takes 10% of all production traffic during the tests.
I'm pleased to see that Microsoft follows academia lead, because we did recovery games at EGI, one of the largest worldwide federation of academic resources, computing cloud resources, 4 to 5 years ago. Mostly focused on security parts, where we actually did an entire security challenges of the sites. By some of our team actually injected not real malware, but actually really enough malware to scroll around the infrastructure. Now you said you're using the pre-production environment, but at which scale do you do these games? Do you that focused on certain applications, or do you do them on the infrastructure worldwide, on your pre-production infrastructure? How is the scale extends to how you do these games?
Well, so currently we run it on, I believe, 4 services, which unfortunately, I think I mentioned this earlier, it's very hard to coordinate multiple teams and convince them to run all these faults at the same time. But basically, we have 4 independent sessions for different teams to run these recovery games. It's nowhere near the scale of, I believe, I don't recall if it's Google or Netflix, but they would do a yearly exercise, something like akin to a military exercise, where entire departments would be involved and injecting faults at the same time. Yes, all right, got it. But we strive to this goal.
Just ask a question.
Sure.
Do you use any specific type of tools that you develop in-house, or do you use open source tooling that can be used for fault injection?
No, so this system from almost the ground up, except for the faults themselves. So for example, some of the network layer faults, we do take them from pre-existing libraries, but the rest of the system is built ground up internally.
So you drew the parallel to unit testing earlier on, and well, if you want to do unit testing, well, you basically have to write your code around testability. And I'm wondering what lessons you've learned about architecting services for fault injection.
Well, so you mentioned unit tests. So I recently actually saw a very I recently saw a nice little animation describing what unit tests look like. And so the image was a door with a sliding lock, but the door was also sliding. So both of the components worked, but when you put them together, the entire system was failing. So this is really the example. We find problems that we just completely didn't anticipate and that are very hard to detect by just writing a unit test that says, well, failover should happen, but does it really? And this is what purpose these fault injection tests serve. I'm not sure if I answered your question. I think I deviated.
How do you architect services so that it's easier to do meaningful fault injection?
Well, I mean, really, we place the fault agents, we onboard as many services as possible, right? So at that point, once we have an idea of which services are interacting with which ones, it's just a matter of technique. You just configure the fault runs as you wish and then run them on the service. I'm not sure if I really know what you mean by designing services around fault injection. Sounds good.
I have also a question. My question is, you talked a little bit about the different fault types you cover, and one of them was some of them were related to stuff like CPU, memory load, and so on, so non-network stuff. So for these type of faults, how do you choose fault locations? Because, I mean, you have like gigabytes of memories and zillions of possibilities to inject your faults, yeah? So for all the non-networking fault types, how do you do this choice of particular fault locations in your test runs?
Well, oftentimes we start simple. We'll just pick one of these faults and see what happens. And if we see that nothing bad enough happened, we're gonna like throw in another fault for good measure just to see if something, basically we keep hitting the system until it blows up in unpredictable ways. And that is when we conclude that we have a good test.
Do you use analytics for that, or is this all manual?
No, most of this work is currently manual.
Question from my side goes in the direction, do you use and do you offer that also for your sort of customers, or this is just for internal purpose? The latest part I've understood is that you do internal quality insurances or whatever, but the first part, as far as I understood, was also in terms of offering that kind of service to whatever kind of customers. Is this right, or did I get it wrong?
No, at the moment the fault injection system is purely an internal tool.
Okay.
I don't know that if there is any major discussions about opening it up to the public as of now.
All right, thanks.
So my question is basically about the fault patterns that you use to inject the system. Do you consider different variations of fault? Because, for example, if you are simulating the CPU hogging or memory leak, do you consider different slopes of a growing resources occupation, or you just inject the fault like it is?
Now, to my knowledge, currently the spike happens immediately. I think within seconds, it's just going to pick it up and then blast the CPU or the memory. So there is no gradual onset of the fault.
Or you're just shooting the system usage to the
Yes.
top and
Yes.
consider that to be
Yes.
the...
As I mentioned, I'm not a core developer on the team, so maybe there are features that I'm just not familiar with. But to my knowledge, there is no such feature at the moment.
Okay, thank you.
Just to keep you busy.
Sure.
All right? So 2 simple questions. How reproducible are your results?
Pardon me?
How reproducible are your results when you do fault injections?
So when we write the regression tests around fault injection, these take sometimes a week or so of tuning, but eventually we're able to get very high accuracy. So if there is a problem, then we'll get a failure, and if not, everything will pass.
So maybe let me rephrase my question. Since the load on your system is continuously changing, from the time you inject one fault and see the results, if I had to do the same experiment again, would your results be reproducible?
So this is actually a very good point. I thank you for that. We're going to take advantage of it. Currently, the regression suites actually run at the same time of the day, so we don't have what you just described. But it would be very good to open that up and try them at different times of day to see what happens. We try to keep them in a controlled time range because since they're running on the real system, this may result in on-call engineers seeing an issue and panicking. So we try to keep the windows very controlled. But it is a very good point.
So let me change my 2 questions to 3 questions. All right? One, what constitutes your definition of an anomaly? So when you inject a fault, what exactly are you detecting?
So when we
Where do you classify something to be anomalous or something to be good enough or a little bit off?
So this really comes down to how we write our alerting. So we expect that a fault will trigger an alert. So for example, CPU pressure will trigger throttling of requests and CPU pressure alert to fire. And these are definitions that are taken outside of the fault injection, and we use fault injection to verify that the system can respond correctly according to these specifications.
You know, you've actually made me ask a 4th question, but I will do it offline. So the last question, so far you talked about injecting only one fault at a time. Now in reality, multiple things correlate to cause a crash or the other. So how do you explore those things?
Well, so this is actually one of the challenges that I was bringing up earlier. And so one of the examples that I brought up is a new feature that we were verifying that an edge case of which was caught during a fault injection run in a downstream service. And so the more teams we can get involved in this and the more teams we can onboard to regular fault injection, the more we can simulate multiple sources of failure at the same time.
Talk to me afterwards.
Sure.
There are groups in Microsoft who do some of these kind of things, and maybe we'll talk later.
Sure thing.
Left-hand side.
Yeah, since you brought up the analogy to unit testing, usually when you do unit testing to verify something, you have coverage criteria. When you stop testing, do you have something similar for fault injection when you talk about verifying the resilience?
Well, so in an ideal world, we would have at least the alerts as a benchmark. So we would want to have faults that would trigger every single kind of alert that we can fire. Of course, this is very hard to attain realistically, but this would be the golden, the North Star really, is to make sure that all the alerts that fire and all service level responses that are difficult to test in isolation are covered by these fault injection tests.
Okay.
So when you're saying you try to trigger every possible alert, do you have any mechanisms to find unknown unknowns? So because maybe there's an alert that you haven't thought of or something, then you probably won't inject faults to trigger that specific alert that you are not aware of. So are there any mechanisms to find this kind of faults or alerts?
So the alerts are scripted, right? So we have a list of them. We write them as monitors on top of our telemetry. So by definition, we could just really pull the source files and see what alerts are configured in the system, right?
So you say you used like pre-production environments for these tests. So
Yes.
what kind of workloads here are actually running on this cloud that you're running your test against?
So let's see, I want to be careful here. I don't know to what level of detail I can go into, but it is running a considerable percentage of production traffic at all times for analysis. So this is serious load. We're talking about a reasonable fraction of our production traffic. So this is not a test environment with one request per hour that someone built and forgot about forever. This is used very actively to make sure that our deployments are ready for production when we test them.
Thank you, Pavel.